In this lecture, we discuss computational techniques for data assimilation. Really, the motivation for this is to give a full year course in numerical analysis, motivated by the problems that we will have in data assimilation, at least computationally, and condense this into about a 20-minute video presentation. So the lectures will be interspersed with various projects, and you can pause the video and work on the projects or come back to them later. And there's also a separate video that's going to discuss some of the problems and mini projects. So a lot of the motivation is going to come from 3D VAR, optimal interpolation, and the Kalman filter update in the 4D VAR method in data assimilation. The 4D VAR and the optimal interpolation involve optimization. They also involve numerical linear algebra, as does the Kalman filter update. For nonlinear problems where we have a solution operator M, we often need to discretize a differential equation, either an ODE or a PDE, to do this. So a rough outline, we'll talk about numerical solution of differential equations, basic concepts of consistency, stability, efficiency, accuracy, local and global errors. Numerical solution for linear systems of equations, both direct methods where we store the entire matrix, and indirect methods where the matrix is not stored, but rather the action of the matrix on a vector is known. We'll also spend some time on optimization and zero finding techniques such as gradient descent, Newton's method, and BFGS. So some philosophy, getting an answer to a problem is not enough anymore. We increasingly require knowledge of the confidence or the error that may exist in this numerical solution or answer in quotes. We want to differentiate between the difficulty of the problem to be solved and the effectiveness of the algorithm used to solve it. In some contexts, the difficulty of the problem is characterized by its condition number. This is especially true when solving linear systems of equations where the matrix, in this case assumed to be invertible, can be assigned a condition number that gives an indicator of how difficult it is to solve with that matrix. We can also talk about the stability of an algorithm. A good example of this is the classical Gram-Schmidt process is actually numerically unstable, but there are stable versions or stable algorithms that do the same task. So some of the basic ideas start with the computer arithmetic. So every time we put computations on a computer, there are errors that are inherent. For example, the floating point representation of a real number x has the property that the floating point representation is x times the quantity 1 plus delta, where in absolute value delta is less than or equal to mu, the machine precision. So the machine precision that we typically work with these days is double precision, which is about 10 to the minus 16. All the arithmetic operations like addition, subtraction, multiplication, and division, when we perform those operations, we have similar error properties. One thing that we are often very careful about when we design algorithms is to avoid what's called subtractive cancellation. And subtractive cancellation is the idea that we should avoid subtracting two numbers of like size. And the basic problem is highlighted in this inequality on the slide, where the terms with x minus y in the denominator are the terms that amplify the error. the terms x minus x over x and y minus y over y, those are machine precision, but the other terms in the inequality, those amplify the machine precision. A classic example of this is calculating the square root of 1 plus x minus 1, and we use a standard trick multiplying by 1 to rewrite this as a more numerically stable way to compute the same quantity. So the MATLAB command that is kind of gives us some information about the machine precision is EPS. So you can always type in MATLAB help and then the name of a command. So EPS will lead you to what EPS does, but also you'll start to see some other commands related to this. We often solve linear systems of equations, and from scalar equations all the way through operators in Banach spaces, we have the Fredholm alternative theorem that says when we solve a linear system, there are either 0, 1, or an infinite number of solutions. So in general, the MATLAB command to solve a linear system is slash. You can either write out the word slash or use the symbol slash. And it generally gives a solution, but one needs to be careful to make sure it gives something that we're wanting. Okay, so conditioning, and where the condition number that we discussed before comes into play, is when we look at the difference between the exact solution of a linear system and a perturbed solution of a linear system. Here we are assuming that A and A plus delta A are both invertible. Okay, and notice that it's natural because of the representation of numbers on a computer that we'd have some delta A and some delta B in general. So the condition number inequality that's derived here, or that's shown here rather, it says that the relative error in X is roughly bounded by the condition number multiplied by the sum of the relative error in A and the relative error in B. So we often try to make use of the structure of problems to do more efficient computation. Among the structures that are important are tridiagonal, triangular systems, banded, and sparse. So among the MATLAB commands for the solution of linear system of equations and related things are slash, QR, and SVD. And note here the difference between the forward slash and the backward slash in MATLAB. So there's roughly two main types of solution techniques for solving invertible linear systems of equations. The first are the direct methods. These generally require that we store the matrix and store the factorization. And we typically try to proceed in a factor solve way, where we first factor the matrix into a form that allows for easy solving, such as an LU factorization or a Cholesky factorization. So here L is lower triangular and U is upper triangular, so we can use backward and forward substitution to solve the linear system after it's been factored. The factor solve paradigm allows us to solve with multiple right-hand side B's with just one factor. So among the MATLAB commands are the LU command and the Cholesky command. So the standard technique for solving with indirect method is the so-called conjugate gradient technique. And if you look at the algorithm here as it's written, what's striking is that we only need to calculate A times vectors. So there's, in the definition of the initial residual, there's A times our initial guess x naught. There's in the loop, there's A times pk. And so as long as we can calculate A times an arbitrary vector and without knowing, exactly, or storing the matrix A, then we can apply these types of iterative algorithms. So MATLAB commands to do things are PCG, which is a preconditioned conjugate gradient technique, and CGS, which is conjugate gradient squared. So here's our first mini project. The first mini project, we're gonna make a a symmetric positive definite matrix, for example, using the code fragment here, and we're going to reverse engineer a problem with a known solution by picking x and then forming b as b equal a times x. For example, you could pick the vector of all ones or a unit vector, anything you wish for x. So this way you know what the exact answer is. And so the idea of this project is to use the direct method first, using the Cholesky factorization and slash to do the solve, and then PCG, the precondition conjugate gradient method, as the iterative method. One thing you might try is increasing the dimension of the problem. In the code fragment above, the dimension of the problem is n, and seeing how the efficiency of the algorithm changes as you increase n. Eigenvalue problems show up a lot, and we'll see them in the stability of solutions. So it's a NP-hard problem. Basically, numerical techniques, they divide the problem into a finite part. The finite part reduces to an upper Hessenberg form, which for symmetric problems is a symmetric tridiagonal form. And then the infinite part is generally an iterative technique that takes this upper Hessenberg or symmetric tridiagonal form and approximates the eigenvalues starting from there. An important decomposition is the Schur decomposition, where A is QT, Q adjoint, where Q adjoint is unitary and T is upper triangular. Among the MATLAB commands here are eig and Schur, eig for finding eigenvalues and Schur for finding the Schur decomposition. So the standard technique for solving nonlinear systems is Newton's method, which is a zero finding algorithm. It requires an initial guess x naught, and then we solve a sequence of linear problems. So f prime of xk will be a matrix, delta k will be an unknown vector, and minus f of xk will be the right-hand side. Then we update and repeat until hopefully we converge. There's a local convergence result for Newton's method, Newton-Kantorovich theorem, and the MATLAB commands are f0 and fsolve and other related commands. So to solve optimization problems, we often use gradient descent with a line search that's outlined here. So the line search is determined by the delta n or gamma n rather, and this is the standard form for the line search. And then BFGS is a method that combines some of the nice properties of gradient descent with the fast convergence of Newton's method. So the second in-class mini project, and you can pause the video after we read through this, is to optimize the cost function which we've provided using different initial guesses and use the MATLAB unconstrained optimization command fminunc. And so there's different options for how to run fminunc, and the idea of this project is just play around with the different options and see which work better. Okay, common task is interpolation of data. It can be XY data, which is basically displacement as a function of time, or we can think of having velocity at y primes or accelerations or some combination of these. So there's two types of techniques. There are global techniques and local techniques, and the global techniques have some difficulty in that they can become ill-conditioned, have oscillations, and they're spurious and so-called Gibbs phenomena. The approximation properties of global interpolant is outlined in this theorem here, and notice that it's somewhat analogous to Taylor's theorem. Local interpolant or piecewise interpolant is commonly used, and a classic example of this are piecewise cubic C2 polynomials, where we combine interpolation, continuity, and boundary conditions, and then there's a simple tridiagonal linear solve to determine the coefficients of the local cubic polynomials. MATLAB commands are spline, ppval, and unmkpp. Another standard operation is to approximate definite integrals. These can be in one or higher dimension. So we've been familiar with these for a long time. We can approximate f with a polynomial. For example, with a linear polynomial, we get the trapezoid rule. With a quadratic polynomial, we obtain Simpson's rule. It's a very nice class of techniques based on Gauss quadrature, where basically the formulas come from determining weights, the wi's, and nodes xi to get optimal order of accuracy. So there's often interest in specific numerical integration techniques depending on the type of behavior we have in the problem. For example, for problems with singularities or highly oscillatory functions. So MATLAB commands include integral and quad GK. So the numerical solution of initial value problems, where we have x prime, which is x prime of t, equal f of x, an autonomous problem with an initial condition x naught, where we approximate the solution at time tn by xn, and in this example, we use a fixed time step delta t. So then the two classic examples, they're both first order examples, are forward Euler and backward Euler. Notice the only difference is where f is evaluated. With forward Euler, it's evaluated at the current value of x, xn, and for backward Euler, it's evaluated at the new value of x, xn plus 1. This means we'll have to solve a potentially nonlinear system of equation to determine xn plus 1 using backward Euler. Both these are first order methods, okay, same order of accuracy. So if we plug the exact solution into the method, what we find is that we get something of order delta t squared from the Taylor series expansion. The difference lies in the stability of the method. So for example, if we take the standard test function f of x equal lambda, where lambda is a negative real number, then we have a step size restriction for forward Euler to have a decaying solution, but no step size restriction for backward Euler. This doesn't mean we can always use a large step size for backward Euler, but it means that accuracy considerations are what drive the choice of step size versus stability restrictions like we have with forward Euler. So the fundamental theorem of numerical analysis says consistency, which means order greater than or equal to 1, and stability, which we just discussed, implies convergence. So among the one-step methods are the Runge-Kutta methods. These are extremely popular methods. Here's a link. If you work with the PDF, this is a clickable link. Okay. So multi-step methods, which are backward differentiation formulas, are good methods, for example, for parabolic problems that have a so-called stiffness. Among the MATLAB commands are ODE45 and ODE15S, which is S is for stiff. Numerical solution of boundary value problems is the standard techniques are to use collocation methods, and MATLAB has commands BVP4C and BVP5C in order to implement these types of collocation methods. For the numerical solution of PDEs, some of the examples are the diffusion equation, the advection equation, and the wave equation. For advection and wave equations, classical methods are upwind, Lax, Wendroff, and leapfrog. We need to combine here for PDEs, time-dependent PDEs, a spatial and a temporal discretization. So there's many choices for the spatial discretization: finite differences, finite elements, collocation, spectral methods, etc. We perform stability analysis, and often one obtains a CFL condition. A CFL condition basically is a relationship between delta t and delta x, depending on the spatial and temporal discretization that gives us stability. So there's a MATLAB command PDE-PE, which solves parabolic and elliptic problems in one space dimension. So the third in-class mini project, you can pause the video after we read through this, is to solve some ODEs. So if you download the files, the test problems here, and run the drivers for Lorenz 63, then you can also run and write a driver for Lorenz 95. You can modify initial conditions, compare solution behaviors. So time permitting, you can write drivers to approximate solutions to some other problems. There's a Stommel-Lorenz model in there and a Kuramoto-Shevchinski equation. You can also download the MATLAB code to solve a shallow water model in different configurations. Okay, so this brings us to our last slide. So the homework is to develop a 4D var cost function for the Lorenz 63 model. Okay, so think of the 4D var cost function that we had on the second slide of these lectures, and you can then form this cost function and solve using the fminunc, which is the MATLAB unconstrained minimization algorithm. So we've used in several places in deriving techniques for data assimilation the Sherman-Morrison-Woodbury identity. What it basically says that if we know how to solve with A, but we have a rank K perturbation of A, then we can use the fact that we can solve linear systems strictly with the matrix A to solve problems with the rank K perturbation of A. Okay, so here's the Sherman-Morrison-Woodbury identity. So assuming invertibility of the perturbed system, which is this term right in here, this C inverse plus VA inverse U, how many linear system solves with the matrix A are required to solve a linear system with a rank K perturbation? So this is with a single initial condition, or with a single right-hand side, rather. So if we have multiple right-hand sides, how many linear system solves with the matrix A are required? Notice that some of the linear system solves don't involve the right-hand side. For example, we don't want to explicitly form A inverse. We want to solve linear systems with the matrix A. So to form A inverse U, we would in fact solve K linear systems with the K different columns of U. All right, well, that's it for now. Remember to check into the other video with the background or a little more information about the projects. And that's it for now.